Hello, this is Mr. McMurray, and we're here at Spotting Bad Science, a rough guide to spotting bad science. If you have not downloaded this PDF onto your device or computer, you may want to do that so you can look at that. I will have this on the screen if you can see that. But anyhow, just like to go through a few things here. Some things, and sometimes hard to tell. We talked about pseudoscience, real science, good science versus bad science, junk science, sometimes it's called if it's not good. How can you tell if it's good or not? And sometimes it's very difficult. Other times it's pretty obvious. But some things to watch out for. Number one, sensationalized headlines. All right, National Enquirer type headlines, obviously, but regardless of any type of newspaper, the headline's there to get your attention, and so they may not exactly be 100% correct in what they say in order to get your attention. A cure for cancer, but if you start reading it, it's like, well, it's showing promise, and in 10, 15 years it may be developed and it may be allowed, but a lot of times that's going to give you the false impression. Misinterpreted results. A lot of times when you're reading a newspaper article, it's by a person who may have been doing sports yesterday, social something else. They may not be very knowledgeable in the subject they're reporting on, and so sometimes they may misinterpret the results of the original study. Or rather than telling you all about the study, they only tell you the parts that will get your attention, and so it gives you a false impression of the whole story. So you've got to watch out for that. Conflicts of interest. Probably a big interest was the scientists who worked for the tobacco companies for many years continued to do experiments in which they showed that smoking did not cause cancer, lung cancer, or any other kind of cancer. But obviously, if it's being sponsored by the tobacco companies, that's a conflict of interest. Any kind of study, for example, if we were studying the cause of cancer, and it was sponsored by McDonald's, it's probably not going to emphasize diet, fast food. Would that affect cancer rates? Well, that's not going to be something they're probably going to want to do. They're probably going to be concentrating on more ways of curing cancer or something like that, which is not necessarily dishonest, but anytime you see a study, you need to keep in mind who sponsored it, who paid for it, who put it on. And therefore, do they have a conflict of interest that they have some reason they want this to come out a certain direction? All right, correlation and causation, we talked about that already, because just because there's a correlation does not necessarily mean that one causes the other. Okay, unsupported conclusions. Sometimes they speculate. They say, well, here's what we found, and we think maybe in the future we'll find this, but that's pure speculation. What they found this time is much more modest and doesn't claim as much. But then they think, well, this will lead to, well, now they're trying to tell the future. And so that's an unsupported conclusion, and they don't know for sure what will happen in the future. So you have to watch out for that. Problem with sample size. If you have a small sample of 10 people, for example, you may get non-typical results. Okay, it's not a good representation of if you had people of different races, different backgrounds, and what different diets, different exercise regimes, extra other things. The larger your sample size, the more likely you are to get a mixture of all those different characteristics, and so they're going to kind of cancel each other out. And hopefully, the only thing that will affect your results is the variable that you're trying to study. So the more bigger sample size, but if you see a sample size that uses 10, 15, 20 people, that's probably not very good. It would be much better if it's a large sample size. But there are some things, for example, rare cancers and stuff like that, that they can't. There is not a large sample size of people. If you want to test acne medicine, on the other hand, heck, there's teenagers all over the place that you could pull in for your study. But for some fairly rare diseases, sometimes known as orphan diseases, because there's not medicines being developed for them and stuff like that, because not very many people have it, it may be very difficult to get a large sample size. There have been cancers, for example, breast cancers. The treatment used to be a mastectomy, and when it reoccurred, the surgeon said, well, we must have left something in there, so we just need to do more and more and remove not only the breast tissue, but even maybe the muscle tissue, and it just got more and more and more. They started more and more radical mastectomies. And one researcher wanted to test that out and see, does it really make a difference? But unfortunately, he could not, because no one wanted to be in the control group that didn't get the radical mastectomy, because they really felt that would help their chances if they did, and no one wanted to be in the group that didn't get the radical or extensive removal. But eventually he got enough people to do that, to agree to do that, and it turned out that the radical mastectomy was not any better at keeping cancer from recurring, and so they were doing really a lot of damage on women because they were doing this radical mastectomy. And had they been able to get enough people who were willing to do the experiment earlier, they could have reversed that trend. Number 7, unrepresentative samples used. You want to try to get people that are representative of sample as a whole. For example, if you did an experiment, say with a medicine on a football team, that's probably not a representative group because they're in better shape and a much different regimen than most people would be. So sometimes if you have a group like that that you use, you may not be representative of the society as a whole. It may not be a good control group. If there's no control group, once again, obviously, you need to be where one group is not getting the treatment, whatever it is one group is, so you actually have something to compare to see if the treatment actually works better than without. No blind testing. Blind testing, the idea, or a blind study, is the idea that patients do not know if they're getting the medicine or if they're in the control group, which is the one without the medicine. And so usually what they'll do is they will give everybody some medicine to take. Some just have placebos or sugar pills, and others are taking the actual treatment. And that way the patients don't really know which they are. Because a lot of times when they try to evaluate the patient's health, the patient will say, oh, I feel much better, if they think they're actually getting the medicine that will help them. In fact, it's called the placebo effect, and it actually has been shown to actually, they will actually feel better, and they will actually improve sometimes. But it's a very real thing, but to try to limit that, both people are giving medicines. Everybody in both groups, control group and the regular group, are giving medicines. Just one of them is getting sugar pills, and then that way the patients don't know if they are in the control group or not. A double-blind study is when even the person dispensing the medicine, the doctor itself, doesn't know. Now, obviously, someone has to know, someone above him, but that way the doctor can't influence it. Are you sure you don't feel better if you're the one getting the medicine or something like that? So double blind is where the person dispensing the medicine doesn't really know and the patients don't know, and that would be ideal. But at least a blind study where the patient does not know if they're getting the actual medicine or the placebo. Selective reporting. This is very difficult to do sometimes, to resist doing. When we look at a result, if we do a lab, sometimes we may have one lab group whose results are obviously not right. Okay. And we may just want to throw those out. But there's a thin line between doing that and just throwing out the data that doesn't fit what you think the answer should be or what you want the answer to be. And so usually if we have a lab group that has a mistake, we try to go back in and figure out what happened. Did they measure it wrong? Or they use the wrong units? Figure out why they got that data to make sure that it's not just that maybe sometimes it doesn't work. And so a lot of times when a scientist gets results back, it's tempting just to throw away some results and only keep these other results that show what they want, and that is not going to give you an accurate result. But the pressure of wanting to get a positive result or a good result, scientists can be guilty of that. Unreplicable, we just said they need to be repeatable. They need to be able to do them again. If other people can't get the same results, then it's not probably a good scientific evidence. It should be thrown out. Non-peer reviewed. If something is published in a scientific journal, it is what we call peer reviewed, which means that other scientists in the same field who are experts in it look at the study and evaluate it and decide, hey, is this good? Was it run? Look at the procedure and say, was this experiment run properly? Did it have control groups? Did it have these things? And those journals and so forth that do that are going to have a lot higher standards and catch things that may not be very well. On the other hand, if it shows up in parade in your family newspaper or some other magazine insert in there, it may or not be as accurate, or it may not be correct because the person reporting on the study didn't really understand how the study worked and stuff. So generally speaking, magazines and journals, medical journals, things like that are peer reviewed by other professors help to and experts in those fields help keep a high standard of quality, or at least encourage that. The ultimate non-peer-reviewed material would be just plopped on the internet. Nowadays, you can plop things on the internet, and it goes out to everybody, and no one really knows how accurate or not it is. And so, for example, probably 15, 20 years ago, when the first one was, there were all kinds of internet urban legend thing going around about aspartame and how it was causing, and various artificial sweeteners causing autism and so forth. And they eventually traced it down to one email that someone sent out, and from there it just basically blew up, and so forth. So I always have to be leery of things that are not from reliable sources. All right, what I'd like for you to do is, after you look at this information here, there is a worksheet on the module called Spotting Bad Science. And I would like for you to look at those and try to see which of these, there's some studies giving you there, which of these problems do they have? Which ones may make them less than accurate because of these 12 things that you saw here. All right, and then when you get that done, you can submit that, and that will be good.